Hello, everyone. Welcome to the last session of the day of the Castle Workshop. We have 3 more talks lined up for this afternoon. And we'll kick off with Nehas Gupta, who is the Principal Applied Scientist at the Inception Institute of Artificial Intelligence. So I think they are still setting up your presentation as it is. So we will be online shortly once they've figured out the technical issues. So stand by.
Okay, cool. Okay. Okay. Yeah, sure. Okay, cool. All set. So, am I audible at the back? No? Hi. Okay, yes, now I am. Okay, cool. So thank you, first of all, Chirong and the organizing committee for inviting me here. I'm Neha. I am from Inception Institute of Artificial Intelligence. We sit right next door on the first floor. And we are affiliated with Group 42, which is one of the largest AI and cloud computing companies in the region. So about 6 to 8 months ago, we started an in-house effort of training a large language model in Arabic, and not just one, but several. And I realized there's been a talk earlier today also about large language models in Arabic. But I'm going to focus on some of the more technical aspects related to data engineering, particularly challenges that appear when we are dealing with Arabic text, as opposed to English text or French or Chinese. And I'm going to talk a little bit more about what are the different branching aspects that we are looking at when it comes to the large language model. Okay, so for some of us who do follow the AI channel on LinkedIn, in the beginning of 2023, we announced that we will soon be launching a 13 billion parameter model for Arabic, which will then be the largest generative Arabic model in the world. And why we're doing this, it's already been talked about a lot, and since 2018-19, there's been a lot of interest around language models. We have also explored different kinds of language models since then, although we started training very recently. We have a lot of downstream NLP tasks in Arabic that we support. So we are hoping that this large language model can then start supporting those downstream tasks without the need for specialized models. We have, obviously, in the Arabic world, faced a lot of challenge in acquiring reliable, good quality annotated data. So we want to use this model to get around that. This has already been talked about before, but a quick overview that the English models are very large. We have GPT and OPT at 175 billion parameters. Bloom at 176 billion parameters actually covers 59 languages, and 4% of its data is in Arabic, right? And then in Arabic itself, we have ARA GPT-2, which is the same size as GPT-2, at 1.5 billion parameters. We have Noor, which was discussed earlier today. And then our model, we have currently tentatively named it Falak, at 13 billion parameters, right? So I'm guessing my audience is already very familiar with these concepts, but a quick refresher, what is language modeling? So for any given sequence in the language model attempts to assign a probability to that sequence. Higher the probability, higher the likelihood of such a sequence appearing, right? So we have two kinds of language modeling. First is the causal, or the left to right, for languages that are written left to right. Language modeling. So we say that given a sequence W1 through Wm, the probability of the sequence is just the probability, the product of the probabilities of every word. And the probability of every word, Wi, is conditioned on the words that appear before it, right? So basically what you have is this massive neural network. Its input is the sequence, W1 to Wi minus 1. And then it's supposed to output a probability distribution over all the words in the vocabulary. So given the sequence I8N, it's supposed to give you a probability distribution overall. So what you would do is, given this probability distribution, you would sample a word, and then you would just feed it back into the input and repeat this process to get a generative model. So this is an oversimplified view of how the massive neural network is generating language. Our model Falak GPT falls under this causal LM paradigm. Then we have bidirectional language modeling, also something we are exploring, which says that a word does not just depend on the words that appeared before it, but a word depends on the words that appeared before it, as well as the words that appear after it, right? So here your input is actually all the words except word I, which is either masked or replaced with some other word. And the task of the neural network is to predict, or basically output a probability distribution over all the words in the vocabulary for that specific position. Okay, and then there are, depending on the architecture that you're using, the objective with which you train your model changes. So we have encoder-only models like BERT and Roberta XLM, which is a multilingual model. In Arabic, we have ARA-BERT, which is a pretty powerful Arabic natural language understanding model. Then we have decoder-only models like GPT and Falak and Noor. And we also have encoder-decoder models, something very important that we're exploring right now, where BART and T5 are examples of this, where you basically take a sentence and you noise it up somehow. You shuffle the words, you mask some words, and you ask the decoder to then reconstruct the original sentence, right? Okay. And obviously, all of these are based on the transformer architecture, as we've seen before. Now, once you've trained the model, then how do you evaluate it, right? The multiple ways to evaluate a model. And when you're evaluating, you can use both unannotated as well as annotated data. So if your data set is unannotated, right, so you just have plain text, but you have to know that the text is clean, it's written by humans, and it's good quality Arabic text, or whichever language you're working with. Then you could evaluate the model's perplexity, which is basically given a sentence S, the perplexity of that sentence is inversely proportional to the probability that the model assigns to the sentence, right? So if you know that your sentence is good quality, then your model should be likely to produce such a sentence. Probability should be high, therefore perplexity is lower, the better, right? And then if you have annotated data, then you could fine-tune this model, right? So there are two ways to fine-tune. Either you take off the last unembedding layer, so this is just a vector. in the hidden size dimension of your model. And you train a tiny classifier, maybe a fully connected layer, and you basically train just this layer on your fine-tuning data set, and you check how well your model adapts, right? So this embedding doesn't mean anything, then this particular layer will be very hard to train. It'll be like training from scratch. But if it is a good quality embedding, then this classifier will be easy to train. The other way is that you take this particular task, like sentiment analysis task, and you frame it as a natural language task. So you ask it, what is the sentiment of this sentence? In red, that's your prompt. And then you give the content, and then it has to predict the label. So again, this is next word prediction, perfectly aligned with how the model was pre-trained. So you fine-tune on the same way, and you test your model's performance in this way. Right? But the most interesting way to evaluate, which is the main finding of GPT-3, is that you don't need to fine-tune. So you don't need to do any kind of parameter updates or any kind of gradient updates. What it's called is in-context learning. You give a prompt, or maybe you don't give a prompt, and then you give a few demonstrations, right? So here, extremely slow service, negative is the first demonstration. The food was delicious, positive is the second demonstration. There's no valet parking, negative is the third demonstration. And then the final example that it has to predict is, I loved it. Remember, the model has to learn what the task is and predict the answer in a single forward pass, no backward passes at all. So although this is called few shot, but it's very different from the way we traditionally understand few shot because there's no gradient updates happening, right? But the important part is that this kind of performance emerges with scale. For smaller models, you don't see this kind of behavior. The model cannot just learn from a few examples. And for some tasks, very interestingly, the performance of the model with no examples is actually better than if you provided some examples, right? So depending on the task, it may or may not use examples well. Right, so a few hard lessons we've learned. First of all, this is a no-brainer. The quality and quantity of your data really impacts the quality of your final model, right? So we are currently at 55 billion tokens. For Noor, forgive me, we have the number now. It's 150 billion tokens for a 10 billion sized model. And for our 13 billion parameter model, we are at 55 billion. Clearly, we need to really increase the data size still. So we're working on that. But more importantly, the data that you have is not just about the volume. It should have a lot of variety. It should have a lot of knowledge. There should not be bias or toxic content or misinformation in your data. But one more very important point is that if you have a lot of compute, we've been talking about the energy impact of using a lot of compute. If you have a lot of compute, then you can't just expect that you throw all this compute at it and the model just trains in 2 days and you get a very good model. That's not going to happen. No matter how much compute you have, you need to let the model cover at least 100,000 to 200,000 training steps in order to achieve reasonable performance, right? Okay, so these are our data sources. Just an overview, it's color-coded by the domain. So we have Arabic Wikipedia, and then we have Arabic books. We have the Common Crawl in Arabic, and we have 3 kinds of news data sets. Arabic news data sets, basically, news from this side of the world. Then we have English Wikipedia, which we have included in 2 ways. As we know, English Wikipedia is way larger than Arabic Wikipedia. So we used it in 2 ways. First, we included English Wikipedia as is, in its native English form. And the other way is that we translated about half of it to Arabic, and then machine translated half of it to Arabic and included it in our data set. And then we have a lot of data from the Beijing Academy of Artificial Intelligence, who have also collected a large amount of Arabic data. These are all tweets and blogs and data from Arabic websites. And then we have meeting transcripts in Arabic from UN meetings, right? So not very large, but very high quality content. We started off with 33 gigabytes of data only, up until now 416 gigabytes of data. Right. So how do we clean data, which is a very important point that I want to raise with Arabic, right? So a few straightforward things. First, Arabic has a lot of dialects. These dialects are very varied, right? Then Arabic has diacritics, right? So these little marks on the top of the word and the bottom of the word, which dictate how the word is not only going to be pronounced, but what its meaning is. The challenge is that different people might use different ways to write the same word, and diacritics are often missing. And the human reader will look at the context and interpret what the correct meaning of the word is in this context, right? But the same is not true for the machine. The second big challenge is that there are a lot of words which are written in English alphabet, even in an Arabic text, right? So if I were to write II as part of an Arabic document, I would write III. I wouldn't write it in Arabic. So which means that embedded English characters, embedded English letters inside an Arabic document could be genuine, or it could be noise, or it could be JavaScript, or it could be anything. So there's no end to the number of rules you would have to apply to clean out English text from Arabic documents, right? So here's this kind of human-in-the-loop kind of process we follow. We have the data set, we sample about 5%, and we apply our current pre-process pipeline on that. Then we sample 20% further and give it to the human to identify these kind of patterns, right? So one of the patterns is clearly if there are no Arabic words with more than 100 characters, and if there are, it's most likely like some URL or something. And then if 50% of the characters are not in Arabic, it's most likely a bad document, right? Then we have these kind of things like removing highly frequent phrases and sentences. For example, your data is from news channels, then the name of the news channel, or the name of the person writing the news article comes up very often across many documents, right? Kind of like the TF-IDF principle, if you will. Right? So we remove all these frequent phrases and sentences. So this, the human gives us these hints, and we integrate it into our pre-process pipeline. We also score the perplexity of this data using these models that we know to be good. We know Bloom and RGPT2 are actually good quality Arabic models. So we score the perplexity and we feed it back into our pre-process pipeline, right? Then one more small thing we do to make training more efficient is to serialize all our data into a way that we avoid any kind of special symbols or new line characters and so on, right? We add multiple special symbols like new line or end of document and start of title, end of title. What this means is now this model is able to pack multiple documents into the same example. As we know, these models have a certain context size. So for example, we have 2048 tokens with which we are training. So you can then pack multiple documents because of these special tags that gives the model hints that a new document has started, right? Okay, this is pretty standard, but just to kind of summarize, we use byte pair encoding. And then we binarize the data so that every example is just a sequence of integers, and every integer is an index into your embedding matrix, right? Okay, so note that our data set is very large, right? And this means that if you're going to train with this data set all at once, it has to be loaded into the RAM, and the RAM is not sufficient, so it will explode. So we usually do sharded training, which means that the data set is split into multiple parts, and at a time, only one shard is loaded into memory and trained with, right? So your one epoch is actually just one shard of your data, right? So to make sure that our pre-process pipeline is also efficient, what we do is we move this sharding step right to the very beginning of the data processing pipeline, right? So instead of sharding just before we feed our data to the model, we shard right at the beginning. So let's say we have D1, D2, D3 are 3 different data sources, and we eventually plan to train also with 3 parts, 3 shards. We'll immediately split all of D1, D2, D3 into 3 parts each, right? And then each individual piece will run filtering and cleaning. And this entire process can be run across 9 identical, independent, parallel processes, right? And then when you have these shards, you will sample one from each data source in order to learn your byte pair encoding. How should you split words, right? For those of us who are familiar with this step. And then once you've applied it, you have basically split all your words into subwords. And this part is also parallel across 9 processes. Similarly, you will learn your vocabulary using a small piece of this data, and then apply the dictionary again parallelly across 9 processes. Once you're done, you will take 1 green, 1 red, and 1 blue shard and combine it into shard 1. Why would you do that? Because remember that the model is training piece by piece, right? Each epoch is one of these shards, which means that every shard should have a balance of all domains, right? Because your learning rate starts to reduce as you keep training. So shard 1 then has an equal balance of D1, D2, D3, as does shard 2 and shard 3. Right? Okay, so this is a small, on the left-hand side, you see a small example of Falak generating text. The prompt is the very commonly used prompt to Donald Trump. And we use it in 2 different settings. As we saw, like some articles have a title, some don't. So on the left-hand side is Donald Trump as the prompt when it's not the title of an article. I used machine translation to translate it into English. This is actually what the model generated on the top, and on the bottom is the translation. So when it's not the title, it's trying to generate some kind of news about Donald Trump, that he does not seem to have full control of the world, and so on. And on the right-hand side, when it's the title, it's trying to describe what Donald Trump is or give information about it, because most likely it's aligning to the encyclopedia part of the data set. All right? But this is about generation. But how do we make sure that some level of control at least applies on the text that you generate, right? So here's what we do. On the top over there, you see the Arabic monolingual data set, which we start with. And we saw some encoder models, right, like Roberta or BERT. So we train an encoder model, which is mainly for natural language understanding, using that same data set. And then we fine-tune it with some Arabic-specific data sets for offensive text or hate speech or bias data set, right? And after fine-tuning, what we end up with is a text classifier that will detect offensive text, right? Now, given Falak, the user prompts the model, and the generation before returning it to the user, we screen it. This is also very similar to what the ChatGPT interface also does. Actually, ChatGPT interface includes a large number of other control mechanisms as well. This is just one of them, a screening tool to detect offensive text. And if it is offensive, we generate again. And if we run out of generations, we just have a backup response to give to the user in the scenario for them to either change their prompt or maybe the prompt itself is offensive and so on, right? So basically, at deployment time, there will be both a decoder model as well as an encoder model running together. Okay, I think many of us in this room have seen that a lot of generative models, when people report about them, there's a lot of cherry picking involved. So you maybe use the model to generate 10 times, and the one time it generated a good response, you publish it or you put it on a social network, right? So the true test of the model, obviously, is in evaluations, and it's still a new field. How to evaluate a model is still not a very well answered question. However, using some of the different tasks that we have, we did evaluate the model. As I talked about perplexity before, lower the better. We see that Bloom, even though it has like approximately 14 to 15 billion tokens of Arabic only, it's actually very good in terms of perplexity, better than us, in fact, also better than our GPT-2. And one reason, by the way, the models that have been evaluated here are all of comparable size. So although the largest model size differ, but when we evaluate, it's all comparable size. So One reason for that is that, of course, Bloom includes a lot of other languages as well. So it's a good multilingual model. So it's able to leverage its understanding of the English language and bring it into the Arabic latent space, right? And then we have this kind of closey task where the model is supposed to predict the next word. So it's not really a closey task because that has words on the right-hand side as well. But here, you have a paragraph, and only the last word is missing. So the model is just supposed to predict the last word based on the paragraph, right? So here, actually, our model does quite well. As the red bars you see. It's still 7%. It's not a very good number. However, it's better than the others. Then we have the blue bars, which is hella swag, which says that, OK, here's this paragraph, and here are these 4 possible completions. So which one do you think is the best? Since there are only 4 options, even a random guess, note that will get, in expectation, 25% accuracy, right? So here, both our model as well as our GPT-2 is very close to the random guess baseline, but Bloom at least gets more than a 35% accuracy here. Right. And then we have the understanding task. These are 2 sentiment analysis data sets in Arabic. Both have 4 classes, so following the same principle, a random guess has a 25% accuracy, and all are very close to 25%. The whole point of showing this chart is to say that even though we have very well-trained language models, they are generating text which most of the time we cannot distinguish from text that humans generate. Still, their performance in natural language understanding tasks is not that good, right? So this gives us a lot of hints to move forward where we are lacking. The first thing we are lacking, obviously, is that we should add English data sets, in fact. It's not that we should just restrict ourselves to Arabic. We should add English data sets. We should make sure that our model is multilingual. It understands English and Arabic in the same space. And that a lot of the knowledge in the world is actually, or on the web, is actually in English documents, right? A lot of it. So which means that if we just restrict ourselves to documents that are either written in Arabic or generated in Arabic, then that's a problem. And one more challenge, actually, that I missed to mention for Arabic documents is a lot of Arabic data sets are the result of Arabic OCR engines applied on PDF documents. Now, here's the problem with that. Arabic is a right-to-left language, right? And when the OCR is applied, sometimes it so happens that the text that you get is in the reverse order. So it's complete gibberish, actually. And there's no way to tell. Within the same document, for one paragraph, it'll be reversed. For the other, it'll be fine. So there's no way to tell also, at least for a non-Arabic speaker, and definitely there's no way to encode rules in the model itself. So these are some challenges that really impact the performance of Arabic models, and we are planning to work towards them. So future work, okay, this is my last but one slide. So our future work is to include more data sources, more variety, and more knowledge. We want to tune our hyperparameters on smaller models only. Tuning hyperparameters on larger models is out of scope from a computational perspective right now. For fundamental NLP tasks, we think that a systematic evaluation is more necessary than ever. Because obviously there are a lot of models, there are too many possible choices of what you can do while training and so on. Then we want to fine-tune for domains of interest, conversational agent, which is ChatGPT, or a search system, or other kinds of, even a conversational system in a specific domain, like a teacher or an assistant and so forth. Then we want to improve our NLU models to identify and remove the sources of bias and misinformation with greater accuracy. We also want to, actually, one more point here is we also want to add some degree of control to the generation that is happening with this model. So for example, you have this huge model, right, 13 billion or larger number of parameters, which takes like a month to train. And it starts to exhibit some kind of bias, you discover that it's exhibiting some kind of bias. What are your options, really, other than going back and retraining the model or putting some, maybe another model on top of it to detect the bias and so on? What are your options? So we want to make sure that there is some degree of control to the user. And we are really thinking seriously about this problem. So if anyone has any suggestions, please, you're welcome to discuss with me. We are also looking at encoder-decoder models, as I said, which might help us to introduce some degree of control in the generation of the model. And evaluate the cost-to-benefit ratio of larger models. So we have trained all the way from 1.3 billion to 13 billion parameter models. And the idea is to see not just the cost of training each model, but also the incremental benefit of going larger, not just going larger just for the sake of it. Okay, that's that. I just want to give a shout out to our excellent team here, flanked by two enablers. We have Go over here, our HPC expert, and our director, Hector. So catch him if you don't like our work. Then we have the NLP team on the top row, and in the middle we have our data engineers and data scientists. And in the bottom we have Narihan is here. We have our Arabic colleagues as well who are helping us with some of the annotation effort. And that's it. Thank you.
Okay, so again, it's time for questions. Does anyone in the audience want to start? Several hands went up. Okay, from front to back. Sorry, so Alham, would you like to go first?
Can you hear me, right?
Yeah.
First of all, maybe apologies for my minimal understanding of Arabic, but I assume that... Thank you. So I assume that, as you mentioned, right, the input sometimes has diacritics, sometimes has no diacritics, right? So do you run some sort of normalization, or you just throw it as it is? Because from what I understand, you're using standard PPE, right?
Yes.
It means that they will recognize that as two different tokens, which, I don't know, might confuse the models.
Right. You're right. We do normalize. So de-diacritization is a very standard step to normalize. We use some modules developed at the Camel Lab at NYU Abu Dhabi. None of us, the development team, are actually Arabic speakers. None of us understand Arabic. But the Camel Lab at NYU does have Arabic speakers, and they have these excellent modules to clean and process Arabic text, which is very, very sensitive to the language. Yeah.
Thank you.
All right, and we...
What do you think the timeline to reach, let's say, normal or something comparable to ChatGPT would be? What's the timeline?
Can I say 100 years? But okay. I think the timeline, if you're talking about Arabic, is pretty long. It's not straightforward. I would pin it at 1 year, if I'm being conservative. And the reason for this is that even, the ChatGPT is actually reinforcement learning on top of a decoder-only generative model. And that means that a good quality decoder-only model is a prerequisite, right? You cannot get around that, no matter how much data your annotators annotate, or no matter how much reinforcement learning or clever ideas you apply. The prerequisite of having a good quality decoder-only model is still not achieved even by a large margin in Arabic. So that's already a very big challenge. So yeah. And one more point to that, I really want to add, I talked about knowledge earlier, which is that, if I ask a GPT model, not ChatGPT, but a general GPT model, that the capital of UAE is, and it'll say Abu Dhabi, right? But this has nothing to do with language. It's knowledge, right? So which means that a lot of those parameters are actually dedicated to knowledge. Now, if your data, even if we add English data or we translate English data, are we adding knowledge specific to the Arabic world into this model, right? Can we ask questions like, what is the population of Al Ain, for example? We can't, no matter how much data we scrape in English and we translate or do other kinds of clever things, we can't. So this is a challenge that we are already sitting with in the Arabic world, which we are trying to solve, but let's see. Yeah.
So does that kind of lead you guys towards doing a lot of the processing, or at least thought generation in English, and then outputting it? Or you're still trying to develop the model purely for Arabic and Arabic, or Arabic apply logic in English and then come back and translate it back again?
Yeah, I don't think translation is a good option, primarily because of this reason that you cannot, even if you translate, if your base model does not know a specific piece of information, it doesn't matter how good your translation model is, right? If the original content is not generated correctly. And that is what is happening with Arabic models, right? So the approach actually is to combine English and Arabic data during training, combine them, and make sure that it's like, and if I can speak both Hindi and English, right? So if I read something in Hindi, I would still know it and still be able to repeat it in English, right? So it's the same analogy, basically. That's what we are trying to achieve. But yeah, that said, we still need a lot of good quality, high quality data in Arabic, which we are still lacking. Yeah. Thank you.
All right, one last call for questions. And just to check, any questions from online? No questions. Then let's give our speaker another round of applause.
Thank you.
Great, thank you so much, Neha. Okay, and then we'll invite our next speaker up. So our next speaker is Professor Muhammad Alhazendi from our neighbor in Saudi Arabia, Kaus University, from the Visual Computing Group. And his talk will be on imaginative AI.
Okay. All right. Okay. First, thank you for the invitation. I'm pleased to be with you today, and I've heard a lot of exciting talks about mainly foundation model, language model, ranging from how to develop them to work in a single GPU to applications that include health and also how to accelerate our workflow. So this is a lot of exciting things. So I'm mainly a computer vision person, but one of the things that we may refer often in this talk is what can be called vision language models. So not everything I will present today can be called vision language models, but it may be in the intersection between these two. And I will start with some skill that I feel passionate about. I have been working on chasing how to develop this skill better for the past 10 years. And I refer to this skill as imaginative AI. And I believe it's one of the important skills that could be of increasing importance in the next years. So, and it may have implications in transforming species discovery, content creation, self-driving cars, emotional health, and maybe more than that. Is any technical stuff? All right. Okay, so before start, I would like to thank students who has been part of some of the work I will cover in this presentation. Some of them were interns, some were visiting students, but most of them are either master's or PhD student in my team at KAUST. So we are all coming from computer vision background. One of the most popular architectures to develop visual understanding is convolutional neural network or deep learning in general. And one of those networks that are popular is convolutional neural network. Now there are definitely better and the other types of deeper models, but this is just one example of those successful models that can enable visual understanding, so that we have an image like a cat, predict cat, have an image like a dog, predict dog, right? But most of these models are designed with a fixed set of lids, like these lids are the classes that we care about, and this has to be defined before we start training. So the point is that this kind of training, it can be limiting in some way, because in practice we might be interested in predicting things that may not be in the vocabulary that you started training with. So, and this is a skill we will need if we want to enable AI to accelerate something like species discovery. Because, for example, species discovery is about having a model that can understand or can imagine possible different species that may exist, and it can understand that this is not exactly, it could be a cat, but it's not one of the cats that I have seen before. And this might flag some species or behavior ecologist expert to take a deeper look and maybe say something and check if it's actually a new species. So, so it is estimated that there exist 7.7 million animals in our planet, according to these articles in PLOS ONE and Science. And only 1 million of those are cataloged, meaning we give them a name. And this means that close to like 90% of them, we don't have even a name for them. We know that they exist because it's an estimate, but we discovered only 1 million, right? So this means that in order to process the world, it's a long way to just understand what's everything that is ongoing in our planet. And we typically want to understand, people, especially behavioral ecologists, want to understand this behavior, identifying what they do and things like that. And this is what we want, right? Such kind of model we just discussed might not be the right thing to do. So we need models that can understand and can say that I don't know, or it can, from a language description, can characterize a new species and tell it apart from one of the species that exists already. And actually language is one of the ways to define those species, new species, all right? So if you look at popular machine learning paradigms, they may be classified to supervised learning, unsupervised learning, and semi-supervised learning. So in supervised learning, we have access to all labels. In semi-supervised learning, we have access to some labels, and in unsupervised learning, we don't have access to any labels. What I'm going through in this presentation is I will go through different stations about this imaginative AI. And what I mean by imaginative AI is AI skills that is trained to learn beyond the seen vocabulary. So we have a vocabulary of things to learn about. How can we enable the model to learn to go beyond, or learn to understand beyond those existing, what we have seen during training. So there is a station for seeing, and this relates the most to species discovery. Creation, that relates to content creation. Driving, it relates to self-driving cars. And feeling, and this relates to emotional health. How do we understand emotions? So there is a lot of work that has been developed to enable visual perception of things, but not necessarily can reason emotionally about what are the possible constructed emotional experiences that may emerge by being exposed to some visual stimuli. All right, so let's start by the first station, seeing. So as we discussed, there exist more than 90% of the existing species are not yet discovered, so we need tools that enables us to recognize unseen species. And this task is called recognition of unseen species, and actually has been referred to in this workshop as zero-shot learning. And this problem dates really the decades back. So even if most of us don't know what this bird is, if we describe in language Barkidocrit is a small bird that have an orange beak and the plumage is dark above and white below, we start to imagine how this bird may look like. And if we encounter that species in life, it's an easy task for us to detect or tell that this is probably the one that we're talking about. So similar to how we were able to just right now right here to recognize this species, even though we may not have known about it before. It could be desirable to build machine learning methods that have a similar scale. Okay, so actually, one of the things that I want to know is actually in 2013, I have a paper called Write a Classifier, which defines exactly this problem. And it is the first paper that enables visual classification from natural language description. So if you read the CLIP paper, which is a famous text language retrieval model, you will find that they refer to this paper as the earliest paper they know that does this type of work. All right, so why this is useful? In real life, we might encounter a bird and out of nowhere it flies away. And we might be interested to know what kind of bird we have just seen. But we don't have access to that bird anymore because it did fly away. We don't have a picture of it. In other situations, we actually have to fly away. Otherwise, we could be a meal to this hungry bear. So in both situations, if you think about this at the world scale, we care about both the bird and the bear and identifying them at the fine-grained level so that we know how many of those species exist and may some of them be endangered. So the more we have access to more accurate information about those species at the fine-grained level, the more decision makers will be able to take more accurate actions to save those species that could be endangered. So imagine that we are interacting with this like bot that loves the environment, and we tell it, hey, I saw a bird that has an orange beak, and then I wanted to ask the AI bot to tell me what could this bird be. We can maybe the AI bot is not so sure what kind of bird because this description applies to many species, and we can imagine be interacting with this AI bot until it knows what it would really mean, and then it can predict the name of the bird and gives us an answer that we are eventually happy with. And maybe you can pick this bird and know more information from a Wikipedia article or something. If you look at ChatGPT, and I actually try to simulate this kind of conversation with ChatGPT, that actually doesn't work. So I struggle to. It asks me actually to give a photo of the ChatGPT, and I told it that I have a photo, will be able to process it, and why did you ask me to provide this information? Can you process it? And it started to still like nonsense, like because it cannot really process any visual information, right? And this is just one another example from one of my friends, Eric Xeng from UC Santa Cruz. He provided actually the URL for his own like image to describe what it is, but it ended up telling it, hey, I cannot do that. I'm an AI model. I cannot really process visual information, right? And it asked it, funnily, can you grab me a drink? So it answers again, I'm a language model. I'm not capable of physically doing things, all right? So the point is, how can we have or make some progress on language models that can be visually, like those visual understanding is improved, or it could be augmented with some visual understanding. All right, so let's go back to this example. So one of the like ways to model this task is to process the like the language description of an unseen bird by a generator that tries to imagine how this bird look like. And if we have such generator behaving as we wish, it shall produce some visual representation that is in line and is grounded. It matches the exact description that we provided, and hopefully in a way that can separate it from other unseen classes and seen classes as well. And the trick is how to actually build this kind of generator so that it works the right way. All right, so this is a reference for a paper from 2018, but until like similar kind of approach has been developed until these days. So one of the key ideas is to there are some like other like the architectural details, but the key idea is to have a generator and the imaginer that takes an input, that language description during training of a scene class, because you train on scene classes, and scene classes have corresponding images. And you test on unseen classes, and for unseen classes, you have only language description, all right? So you train this so that you have this GAN model. This GAN model is trained with these two layers, the generator and discriminator. And the discriminator is trained to trick the discriminator to believe that this image is real. And the discriminator is trained to tell apart images that comes from the training set versus images that are produced by the generator. In addition to training the generator to trick the discriminator to believe that it's real, meaning enable this red fake LED to be red, or encouraging it to be red, to be green. It won't also be predictive of the corresponding scene class. So there is an additional head. I think it doesn't. So there is an additional head in addition to the real fake head. That is over scene classes. So I want to say, hey, whenever you generate visual representations for Barkidocrit, I have a pen here over the second head that is named after this Barkidocrit, so I want the model to predict that corresponding class. So this is a way to make the prediction or these generations more respecting the textual input, all right? So this is how this is one of the key ideas. I will show you, like, then in the next stop, I will hop back and forth about this and show you how they influence one another. Now we get to the second stop on creation. So what I wanted to show is that explicitly, from the past slide, that explicitly modeling imagination, like, because this generator tries to model this imagination, right? So if you think about seeing unseen classes, understanding unseen classes, and relate to relate that to creation of novel content. So recognizing unseen classes is about understanding the unseen. Producing novel vision generation is about creating a novel unseen, right? So they are relatable. And in the next few slides, in the next slides, I will show you how they are related. So I'll start by here in the Imagine to Create by covering this CAN model. It's a model we proposed in 2017 called Creative Adversarial Networks, and it tries to encourage GAN models to go beyond training styles, like scene art styles. And the idea is inspired by this wounded curve of human creativity. So this wounded curve is proposed by Colin Martindale, who is a Canadian psychologist, who's trying to study human creativity. And if you look here, the x-axis is novelty and y-axis is likability. And he's showing here that if a human produces creative content, it may follow something like that. So if the work is not novel, people may not like the work, but as novelty increases, people will start to like the work more and more, but not for too long. When the work is too novel to understand and to relate to existing concept that we know, that such lack of understanding will lead to lack of appreciation. All right, and the idea is how do we model such kind of deviation in a machine learning model? So one of the early attempts is to train such a GAN model that we just talked about, like train a generator to trick a discriminator to believe these images are real. But in principle, this GAN model has no explicit motivation to encourage these generations to be different, to be any different. It tries to basically imitate the training data distribution. So what has been proposed in this paper is to add a loss function that explicitly promotes the generative model to produce something different. How does it do that? It adds an additional head over existing art styles. So these are the art styles that humanity have ever encountered, including abstract art, cubism, impressionism, high Renaissance, and others. And so we add another loss, and this loss is for not only predicting this is real or fake, also to predict that this is what art style this image belongs to. So if I have an image that belongs to, that's like the Mona Lisa, I want this to predict that this is real, and also to predict in the style classification head that this is the high Renaissance art style. This is from the discriminator training side, but this is not. I like it. Sorry. This is not what we want the generator to produce. So if you look at this, this will produce if the generator were to produce something like this, it will produce something that whose response over the style classification head will be 100% on high Renaissance and almost zero everywhere else. Right? So it's easy to classify to existing art styles. And this means likely to be seen, but this is not what we want. We want the model to produce some style that hopefully did not exist. And the question is, what may characterize this kind of novelty loss? So instead of doing that, we encourage the generation, add a loss function to the generator to encourage the generations to be hard to classify to existing art styles. So I wanted to confuse the discriminator I wanted not to be able to tell which style class it belongs to. And this is quantified by encouraging the entropy to be high over existing art styles. So this is how, and in the meantime, because we can produce a random image, for example, and this random image could be entropic. But there's another trick here that we encourage this image. This image has still to trick the discriminator to believe this image is real. So there are two loss functions that enable this to work well. All right.
I like it.
It's
really cool. So who painted it? A machine.
It's actually the first work of art made by AI to be sold at Sotheby's. Sorry, I'm late, I got caught.
So this is a scene from HPA Silicon Valley, and that it demonstrates one of the artworks that were produced by our system that time. The work was at that time exhibited at large in the biggest, I would say, art exhibits, and got a lot of media attention and by MIT Technology Review and many other places. All right. Very recently, we proposed a follow-up in the Computational Creativity Conference called a paper called Creative Work Adversarial Networks that is actually nominated. Didn't get the Best Paper Award, but it is not nominated for the Best Paper Award. You can think of it as an improved version of this method, but based on more like novel architectures. And the idea is to build a dynamic graph over existing art style centers, C1, C2, C3. I won't have time to go over the technical details because those exist in the paper, but the key idea is like this. So it built a dynamic graph that connects scene art style center in green to produced images in the current mini batch that are colored here in orange. And it actually formulates a random walk class that starts from every scene class center, goes through the generated orange images, which are the current images produced by the generator in the current mini batch, and encourage the landing probability over scene art styles to be entropic. So no matter which class you start from, if I go through generated examples that I want to be novel, I want this to be I want to make it for the model hard to know where it starts. And the intuition behind that is that I want to model that as a deviation loss. I want those models to be communicating with one another. The difference between this and the previous loss function, which is just high entropy over every single example, is that this is a loss function that collectively enable message passing between those novel images together. And this encourages them to be better spread in the space so that these generations are less suffering from mode collapse. So they are encouraged somehow to be more diverse. All right. So this is just an approximation produced by our experiments. Here we show the nearest neighbor distance from the training set for our models, for some sets from our model, and also some of the baselines that are based on, all of them are based on style-GAN architecture. And the contribution here is more the loss function, more like the loss function itself. All right. Okay. So one of the things that so the model will capable of producing images that have a higher nearest neighbors distance from the training set, and this can be used as a metric for novelty. And the y-axis here is likability. So the higher it produces images that are more distance and more likable compared to the baselines. And we wanted also to see if actually these generations are meaningful. So to do that, we asked people to annotate constructed emotional experiences in response to the visually generated, the generated images. So we asked people, how do you feel about this image? And ask them to write in no less than 8 words what they actually have felt. So if they felt nothing, they will choose something else and say that this is not a meaningful image. But if they have actually meaningful emotions, they have to pick one of these 4 positive emotions, 4 negative emotions, and then write in description what they actually felt. And what we observed is that these generations managed to create diverse emotional experiences. And you can see under each emotion, the most frequent words used to describe the constructed emotional experience. So this seems that this AI model were capable of also constructing emotional experiences that we can communicate about it in meaningful language. All right, so you can see that this is an example of contentment, fear, like amusement. This is about ancient Egypt, and so on. All right. So going back to the seeing station. So these two are connected in some way, and if we revisit the one that we just talked about, but from visual perception perspective, from the perspective of recognizing unseen classes, let's rethink about generating visual representations But in the context of species discovery or recognizing unseen classes, let's rethink about this as producing visual generations for unseen classes. In this slide, you can see Barkidocrit, Christidocrit. Barkidocrit is a seen class because this is x-axis is novelty against seen classes. So seen classes are on the far left. Y-axis is how well you can tell these two classes apart. So we have a language description of Christidocrit, which might be very similar to this because it's both have orange peaks, both have plumage that is dark above and white below, and there are small differences that relate to the curvature that are coming from the top of the bird. And we're giving a generative model this language description. So if this generative model is not good, it might tend to collapse its representation to one of the classes that it has seen already, because there's a bias on the model to collapse to classes that has seen than to classes that the model hasn't seen, right? Because we don't have training data for unseen classes. So the question is, how can we push the differences between these two classes so that the model can distinguish between them, but we don't want this visual generation to be pushed too far so that we produce something far away, but it doesn't mean anything. It's not grounded to the text description. Because we understand concepts like red beak or orange beak or plumage from classes that we have learned. We understand it, the pieces and the parts, the composition of the units, perception units that we had from getting exposed to unseen classes is what enabled us to recognize well unseen classes. So one of the papers that we presented at ICCV 2019 was trying to model this. So hallucinate, we came up with a hallucinative function that tries to explore the unseen space of visual generation. So imagine that during training, you have access to those 1 million animal species, and you want the model to explore beyond that by some hallucinative function that explore the space that does not overlap with classes that I have ever seen. And then this will produce TH. TH will produce visual generations. I want these generations to be realistic, so I want to still trick the discriminator to believe these images are real. In the meantime, I want the model to know that this is not one of the seen classes. So I want to make the model to classify the visual generations of hallucinated unseen classes. I won't make them hard to classify to any of the seen classes, meaning producing entropic responses over seen classes. Same loss function has been used to encourage promoting novel visual generation in art is applied here in a conditional way to enable the model to be able to double its performance for separating these two very similar classes. One is seen and the other one is unseen. So the difference between these two curves is just the additional loss function, right? And this additional loss function does not require any labels. It does require just access to some hallucinative exploratory function that explore the space of unseen classes. All right, so recently in 2023, we have made some development on top of this by encouraging this random walk loss that we talked about earlier. Same thing, but we made that conditioned on the length, these hallucinated attributes. So this will generate the orange images, and we have seen class centers that are also generated conditioned on the language description. So we add the loss function to encourage the model to be capable of separating unseen classes that are very similar to seen ones, right? How do we do that? Define a random walk loss that starts from every seen class, goes through the orange points, which are generations that comes from hallucinated unseen classes, and make the landing probability of that random walk loss to be hard to predict or to produce an entropic response over seen classes again. So this encourages the visual representations of these unseen classes to be more separable from these unseen classes to be more separable from seen ones. And we Yeah, we have results that shows that adding this loss function improved on top of the earlier paper that I just presented, the ICCV paper. So we have, this is more like an improved version, but it's a message based on message passing between those generations. All right, so this is this is what we achieved so far. This is about species, so like species only. I showed it to you with this video earlier, mainly to share with you that we also worked recently in a paper we called MammalNet. We submitted it to CVPR. It seems that this has good reviews. So MammalNet is about what? MammalNet is about building the ultimate hope is to build the ImageNet of behavior ecology. So it's a video data set that has, like so far, hundreds of animals, 13 behaviors. This includes eating, drinking, fighting, mating, and others. And the goal is to basically accelerate. When we talk about animals, we talk that we are interested to identify them. Not only identify them, we want to understand what they do. And what they do is about recognizing their activity, right? So we created a set of 500 hours of video that has these activities of all these animal behavior pairs. And we're aiming to expand that to more. So this is the team. So this is a joint collaboration between like computer vision experts and and also behavior ecology experts. So and it's a collaboration with Anya Rubrick from UC Berkeley and Sarah Perry from MIT, and from Research Center at KAUST, Michael Berman, the director, and Darren Coker, the research scientist. Blair also is joining us from Max Planck Institute of Animal Behavior. So it's still, I would say, we achieved milestone, but still there's a long way to go. Driving. So self-driving is very important to, and we want to get to this, to get this milestone, but still there are challenging to achieve this and make it achieve the level of safety and that we desire. There has been a lot of progress, but one of the main things that if they do work quite well, maybe in restricted area, let's say we have good models that works only maybe in certain cities. In San Francisco, if you take this same model here, or in Saudi Arabia, it may not work because the domain is out of domain, right? So we want models that are capable of understanding well beyond what it has seen also in this space. How that can be modeled, how the same idea can be modeled for self-driving cars. So imagine this model that it is more like a variational autoencoder that takes the history. The history is XY coordinate of the car, the ego vehicle and surrounding vehicles, and you want to predict the future trajectory where this car should go. So this is a motion forecasting problem, one of the fundamental problems in self-driving cars. And one of the things that is modeled in self-driving car is future intent. So if you are at an intersection, and given whatever history you have, there are multiple futures. You can go right, you can go straight, you can go left, you can go right first lane, you can go right second lane, you can go right third lane. And this is what modeled here by this random variable z. If you look at P of y given x is the history, m is the map information, z is the driving intent. And for every driving intent you sample, right, you get a different future. So what we propose here is to hallucinate the driving intent, ZH, which is basically a mix-up of two existing driving intent, two latent driving intents. So Z is usually a discrete latent variable of 25 different intents. It's one hot vector, have 25 dimensions. You pick one that's set 1, 0, and one cell is 1 and 0 everywhere else. So what you do for a hallucinated driving intent, you have to feed that also for every time step because it's autoregressive. So if you want to predict the future 6 seconds, you fix that driving intent. In order to predict hallucinated driving intent, you pick two driving intent Let's say we have 25 intents, and pick intent number 1 and intent number 5, and switch at a random time step from one intent to another. You will feed that to generator. It will end up produce a trajectory that is produced by mixed latent intents. And you want that to trick the discriminator to believe that it's real. And you have another head that predicts which intent this trajectory is coming from. So you want the model to make it hard for the model to predict which intent this trajectory is coming from. So this is the additional, and this managed to, compared to the baseline trajectory plus from Stanford, it reduces the broad boundary violation by 50%, more than 50%, from 19 to 9.22 for 6-second prediction, and more than 27 prediction reduction in final displacement error. All right, so the final station is feeling. So this is vision language. This is more like vision language model that can talk about our emotions. So we collected 3 data sets over the past 2 years. That Artemis 1 and Artemis 2. Artemis 1 was in collaboration with Stanford, and I was visiting there at that time, and École Polytechnique, and Artemis 2 and RT-Lingo, Artemis 2 appeared at CVPR this last year, and RT-Lingo appeared at last MNLP, which was at Abu Dhabi like last December. And these are more like what? It's a data set collected on more than 80,000 visual stimuli, 80,000 images. For each one of those, we collected more than 5 language descriptions of the visual stimuli that has been constructed. So we ask people, how do you feel? And they pick a particular emotion. And then they describe in language what makes them felt that way. Like, for example, this is a picture of, I can feel in awe if I see a picture of a beautiful waterfront. I can imagine myself sitting by the water listening to the birds, right? So this is not just telling what's in the image, it also reflects on on the distribution of possible emotional experience that may happen. So this is, and this is just some example that characterize the differences between these two. So this is these 2 images from conventional captioning dataset and effective captioning, effective text description on top of images. So you can see here, these are images about birds. A small bird is on top of a big page, a small bird walking on the grass next to a body of water. And on these are the standard data that is collected. In Artemis, we collect data like this is a picture of a bird that gives me hope. This is a pale color palette of water color painting that's very relaxing, and I imagine myself sitting by the water listening to the birds. This is the interface we used, the same one we used to collect emotional experiences for generated images. These are the distribution of constructed emotional experiences over the 80,000 images. These are more than close to 500,000 language descriptions, which is closest to COCO dataset, one of the most popular datasets, but in non-effective captioning. So in CVPR 2022, we somehow introduced an improvement on top of it, basically to balance the data set to include both positive and negative emotions. We found that there is emotional bias in the original data set. So we found a contrasted data collection approach that mitigates that bias. And multicultural version. So in MNLP last year, in December, we presented a data set that includes close to 500,000 Arabic captions. This is the work. It was a collaboration with University of Notre Dame and Kenneth Church from Northeastern University, and back then it was at Baidu Research. So the point is to do the same thing, but in multiple languages. We collected the same thing on Chinese and in Arabic. So this is, to our knowledge, the largest available data set to study emotion grounded to visual stimuli for these 3 languages. So I would also say that this is the largest data set for real Arabic captions collected on images. I don't think there is any other data set that have this scale these days. All right. So you can see that interesting thing is that you can understand the cultural differences. Some visual stimuli might enable someone to feel excited, like this image that might feel that is coming from the Bedouin culture and maybe from Arabic culture. This is something satisfying, but maybe not so much for English-speaking culture and Chinese-speaking culture. So Arabic data was mainly collected in Egypt and Saudi Arabia. Chinese data was collected in Beijing. English data mainly the US and Western world. All right. So we trained models that can enable captioning, multicultural captioning. So given the image, you can actually train a vision language model. This is start to come up. Vision language model that can predict the distribution of possible experiences out of visual stimuli. You can have a transformer head that predicts what possible culture will feel given like a text. So this is a language-only model that predicts emotion by 3 transformer heads, 1 for every culture, 1 for English, 1 for Arabic, 1 for Chinese. So you can see, for example, a beautiful girl holding a Jesus cross stomping on the devil. So you can see that this is predicting more positive emotion for English and Arabic. Because the focus was there in Jesus, and maybe for Chinese the focus was another word, maybe the devil, because this concept maybe is not as dominant. You can see here the man looks like he's drunk, and since his expression is so wired out, this for English and Chinese was more like positive, but for Arabic it was sad. All right, so you can see that it kind of makes sense, right? These are representing of some of the culture differences that come from the data, and the data we made sure that every culture is representing itself. So English data is created by English by this culture. Chinese data were only collected in Beijing. Arabic data were collected by Arabic speaking people in Egypt and in Saudi Arabia. So you can see, but when it comes to babies, like everybody agrees, right? All right, all these data sets, by the way, are publicly available, so you can use it if you found it of interest to your problem or your research. So this is where we are. Just some few concluding thoughts on the future. One of the interesting things that we have this, I'm not sure if you have heard about the no language left behind model by Facebook, which is a model that can translate between 200 languages from across 200 languages from any one to the other. And it's a very large model, and the point is no language left behind. We want language model to be inclusive for all cultures in a sense. And the point that I'm trying to make is how can you make the same point but for vision language models so that no culture is left behind. You want to have models that can respond to a visual stimuli, that can know how we feel in correspondence to visual stimuli depending on which culture we're coming from. So maybe you want to have to create an art like structure or something like that you want it hopefully like construct positive emotional experience for as many cultures as possible. It's hard to do that without mining from the data what people actually feel, right? And having a data like this might enable us to study more cross-cultural psychology, cultural psychology, and more. So because you will tend to know what different cultures agree on, and what maybe not too much, or yeah. So one of the things that we developed at CVPR last year is visual GPT model, which is a kind of a vision language model that enables us to distill knowledge from a GPT pre-trained model into a model that can talk about images. I won't go much, the code is available, but the point is how to do this we have a GPT-2 model which is fluent in speaking, but it's blind, it doesn't see anything. So how can we design a gating function so that it can make it work? And this is important. Why? In like a medical application, you want to generate medical report, for example, the data is typically limited. So how you want model to train to produce this with limited data. So this model is trained with, is taking pre-trained model from a GPT model, in this case GPT-2 because it was the open source version, but it can be GPT-3, it can be whatever is available, and it designs some gating function. This gating function is gating between the knowledge from the pre-trained initialized models and the attention to the image. So it tries to, it tries as much as it can not to disrupt the knowledge of speaking that GPT-2 has already, but in the meantime, it tries to enable it with the least effort to talk about visual stimuli, given images, right? This can be useful for multicultural thing, because imagine if you rethink about the no language left behind into the no cultural left behind. We collected this set for 3 languages, and it took us more than 2 years. So if you want to extend this to many languages, it is super difficult, like financially and anything. So we want model that can pick up quickly, that can scale quickly. Let's say if you have few percent of the data, and which is the same point that this model, this Visual GPT is trained on, right? Visual GPT is trained on what? On 1% training data, 0.5%, 0.1% training data, the image caption pairs, right? So we can rethink about how to get to this milestone of language model that can speak, that can talk multiculturally about the visual stimuli in 100 languages, and it's hard to make this happen without having few shot capabilities, right? Few shot vision language model capabilities, right? Yeah, that's another thing that we're working on right now. I think we will submit this paper to CVPR, is an effective chatbot that can have a conversation between 2 people on a visual stimuli, starting with a debate. One is positive and one is negative about visual stimuli. So starting from the image that we just talked about, we can imagine having a visual, like collecting data between 2 people for the sake at the end of informing a blind person, the questioner doesn't have access to the image, but it can ask more and more questions to an answer who have access to the image. And for the purpose of what? For the purpose of having the questioner who is blind to decide on their own constructed emotional experience at the end of the conversation. So you can think of this as a step beyond what we just talked about, where we want to have a conversation between 2 people, right? And we want to have a dialogue model, an effective visual chatbot that can have a conversation for the purpose of constructing emotional experiences. So we collected this data set of 30,000 dialogues, and it's not released yet, but it's for this purpose. And if you have access to the data, you can actually train a chatbot to make it more likely that the person, that a positive emotional experience is more likely to be constructed than a negative one. So you can actually steer chatbots to drive more positive emotional experiences, right? And if you think that from mental, this is a team from, this is a collaboration with Stanford and with Google Brain team. And this, I think this project is close to conclusion, but we want to scale this more. But we're now working on how to make emotion-aware video language model that can be helpful to predict mental health problem like depression and like autism, from therapy sessions and things like that to early detect mental health issues and problems and things like that. We can also do generative model, I think, extend this vision language model to enable content. We created this data set of 7 million stylized model that can be used for generative models in the metaverse. And you can imagine connecting it to vision language models to localize an object of interest in a 3D environment, like, for example, facing the couch, the right chair, or something like that, or pick me the cup on the table closest to the door. And if you have that in an environment, you can then ask a robot to go pick up this cup and maybe make you a cup of coffee. So what I'm trying to bring to the table is getting back to this idea of, can you ask a language model like ChatGPT to give you to grab you a drink, right? And in order for it to grab you a drink, you need a vision language model that can understand visual scene, localize object based on the description that you want to describe, and act in an environment. And I think this can be an exciting future direction for vision language models. And species discovery, as we discussed, and drug discovery. I think this is the last topic. Like, one of the things that I found also exciting to conclude with is also drug discovery. Why drug discovery is also held like one of the exciting directions is that you want to predict a drug sequence that matches a particular protein, right? So that it hopefully binds with it and solve the problem you're talking about, right? The problem that relates to specific like disease or something like that. People in drug discovery do what? They take two cells, one is good and one has a defection, and try to see what are the differences. And maybe by some practice they find the protein that has a problem. And then to cure or to predict the drugs, they try to find the drug sequence that mutate that protein to go back to the normal state. And if you have models that is trained on all possible drugs, protein drug pairs, those that bind and those that don't bind, we can have generated models that can predict drug sequences, and maybe this has a potential to also accelerate drug discovery. There is some data, like one of the famous, this is actually the, Jacob is actually one of the transformer authors. So he started a company on working on building the first biological computer, so which is exactly what we're talking about. Given a code, given a function, can you produce RNA molecules that lead to the intended desired biological function that you want to have? And these are the references for everything I talked about today. And thank you.
All right. So looking at the clock right now, we might have no worries about it. We should have time for one or two questions from the audience. Does anyone want to take a stab at the first question? Okay, go ahead.
So if we look at what we spoke today in terms of imaginative, we know that there's a lot of improvement in terms of language models, and there's a lot of improvement in terms of visual models. And there are models like Clip and Align that are also like vision language models. So the difference in this whole idea on all these sectors is the imaginative part, that we would like to make them open vocabulary to even instances that or classes, categories that have not even been seen. So what is the major challenge? So in all these examples, the Gyan part is the generative part, which will link the two in terms of imaginative, right? So what is the major challenge here, common to all of these examples? Is it that these generative models can only, because most of them are learned in cartoon or paintings, and like the real aspect is what is lacking? Is that what is the challenge?
I would say it's not one challenge, it's multiple challenges, right? One challenge is basically the bias that might exist in the data set, right? So if we want to really go after this challenge of using AI one day to accelerate drug discovery, to be in the loop with experts, right? We want these models to be aware of the existing species, right? And those species, even those that we know their name, right, follow a really long tail distribution, right? So the one challenge is how to make the model hopefully equally capable of telling that this is a seen versus unseen no matter what frequency or it has during training. So this is one challenge. Usually in the literature, each one of these problems is studied separately. Long tail separately, and few shot separately, zero shot separately. But the reality is actually all of them happened at the same time, right? So each one of these is a challenge, and as a community, we break it down into these domains so that we can it can make approaching it easier for us. But if you want to get into really some the wild reality, I think it will get around to problems like how do we make the model more capable of predicting or reducing the bias for head and tail, and there are multiple dimensions of those. It can be head and tail over classes, but it can be balanced, but it's still at the same time the model is more biased towards men than women. This is also a challenge. So there are also some issues that relate to biases that needs to be handled. So the imaginative skill can be studied like depending on what task we care about. So if the problem is adapted to the species discovery, maybe we'll just focus on the vocabulary of species, and we want to care about being able to know which one of these species has been seen for sure, and reduce the bias towards the tail, and to improve the model's ability to tell apart a scene from a scene one, which gets more challenging when it's a long tail problem, because it gets more difficult to tell which one is seen and versus not seen.
Thank you.
Yeah.
Okay. Any more questions from the audience? If not, I have just one hopefully quick question, which is I think I come from a computational and systems perspective, and so my question is going to come from an angle of basically cost and efficiency. And it is my traditional understanding that most models in the visual space have nothing is free in computation, but it's not been as pressing a challenge as it is on the language model side, where you often see imbalances like a language model as an encoder could be a lot larger in both parameter size and computational cost than the visual part of the model. So especially towards the end, you talked about some of your work like visual GPT. Like, are you seeing in your experience or work issues where say the average higher cost of these language models is upending your assumptions about how long it takes to train or how long it takes to create one of these models, right? I'm curious to know your computational perspective.
For vision-only model or for vision language models?
I'm basically saying compare on the one hand a vision-only model versus a vision language model. The addition of the language part, is that dramatically increasing your computational requirements, or does it remain about the same?
I would say it depends on whether you are training them together or not, right? So if you're training them together, you add to the complexity of training the language model, processing the visual input, and this makes it a little bit more computationally expensive than training the language model alone, right? But one can think that that vision can also be an additional. We have English, we have Arabic, we have Chinese, we have vision. So vision can be also another modality that maybe can be more detailed, and we can, in the context of visual or multimodal transformers models, right? We want the model to be more predictive of the future, and these futures that we want to predict next may not be only words. It could be the next few videos. It could be a video we want to generate. So it can actually get actually significantly more expensive to process all videos on YouTube than to train a corresponding version in language. So it can be easier to break.
No, I see where you're going, right? This is the original straw man I had in my mind was, okay, you take something like a GAN or a diffusion model, and then there is an embedding somewhere that's going to feed feature factors somewhere into the architecture, right? But here you're saying that what if there is a for example, a prompt model that has as one of its attention hits, right, the visual images, right? So that's an architecture where I can see that in addition to a sequence, you have an image as input, and then what you generate beyond that, is it words, is it other images? That seems to be a very much unexplored space. I'm not sure if I'm reading your thoughts right here.
Yeah.
Okay.
Exactly.
But that is an intriguing thought, right? And I could imagine the computational cost of that is definitely going to be on the high side, but that's probably where the opportunities lie. But keeping in mind that the theme of this workshop is sustainability, that's also where the work needs to be done to make it tractable.
We shouldn't do that.
No, I'm kidding. I mean, the whole point of sustainability is to make the expensive sustainable, rather than say, oh, we shouldn't do it because it's not sustainable.
You know what? I think there is there's a new exciting direction of what is called model editing, right? So you don't want to train, as you said, right, GPT models again and again. You want to train it up until, let's say, 2021, and you want to edit it to update its information for the year that has just passed or something like that. So how do we just edit the model so that it doesn't forget what it has learned? And just the computational cost in this case is whatever left, not the knowledge that it has been trained on already, which currently the practice is far from optimal in that sense.
All right, then thank you. Let's thank our speaker once again. Okay. And with apologies that we're running about 15 minutes behind schedule, but I'd like to introduce our last speaker, Professor Alham Fikri from our very own institution, BZUAI, and he will be giving a talk on community-based AI research. Great.
Hello? Okay. It works. This is true. Okay. This one? Right, so good afternoon, everyone, and thank you for the opportunity. This is going to be the last talk today, so it's not going to be technical, it's not going to be mathy. So I would like to have discussion about NLP in terms of multilingual research and how would we collect data sets, specifically where we use collaborative movement to gather NLP data sets, right? So as a background, I think we can agree that currently NLP is moving so fast, right? A couple months ago, we have ChatGPT. It's kind of like shocked the world. We have for the image, we have like Stable Diffusion and other types that are capable of generating cool images. But in terms of NLP itself, the progress is actually not universal, right? So basically, when we are talking about English NLP, we can see a lot of practical usage. We can see a lot of application, from translation, chatbot, image to text, text to image, grammatical error correction, captioning, basically whatever you can think of, usually it works for English, right? But then let's consider Japanese language, for example. We have more than 100 million speakers. In terms of NLP technology, we are losing few components, right? And for the components that we do have, the quality is usually not as good as English, right? But then let's introduce another language, which is Javanese. It's only one letter difference in Japanese, but it's completely different language. It has similar number of speakers. It's almost 100 million of speakers. It's a huge language, actually. But, have you ever heard about NLP technology for Javanese? Well, you can translate from Google Translate, but I think that's about it. I don't think we have any other NLP technology for this language. So a little bit of statistic, right? So we have 7,000 languages across the globe. Majority of them were from Asia and Africa, whereas the least amount were coming from Europe, yet the NLP research are focused on the European one. So that's kind of the imbalance in terms of NLP progress. And so this is a statistic, basically, how many NLP research compared to the population. So on the left side, for example, we can see that we have a lot of research divided by the number of population, the number of speakers, for example, in English or Chinese. But if you compare it for African language like Hausa, the number is less, right? The right one here is quite similar, but it's for Indonesian languages. The red one is the Indonesian languages. The blue one is the European. It's also telling the same story. Right, and not only about the research itself, but it's also about the people itself, right? So this is a real picture taken a few months ago from EMNLP last year. Here, this is the number of submission by country, like how many people from this country. Majority were from China, US. We have a couple from as you can see here, UK. But I mean that's about it, right? If you want to find, where is the author from Africa, well, you're gonna find, it's very hard to find. Or where you're gonna find author from Southeast Asia, it's very hard to find, right? Despite, someone says that no language left behind, but in practice, language do left behind, right? Because, we only focus on these 200 languages. So you actually left behind other 7,000 languages, right? So in terms of NLP research, the research currently is available only for this 100 to 200 languages. I am talking about models like MT5, Bloom, XGLM. These are models that you can use. They only cover these languages. In terms of data set and benchmark, Extreme, this is all multilingual data set. They also cover usually these 100 languages. And one of the reasons, this is not the only reason, but one of the reasons why these languages are left behind in terms of research is actually the data set, right? We don't have enough data set to actually do something meaningful, especially when nowadays NLP technology uses a lot of data set, right? It's very data hungry. This is similar plot as previously. So basically, you can split languages across 10. If you exclude the extinct one, which is, it's extinct for a reason, but you can plot them into 9 different categories. One is depending on how many speakers there are, and then like the status of the language, right? So basically, the blue circle is like how many languages belong to those specific cluster, and the red one is whether this resource is available from Hugging Face. So Hugging Face is, for those who are not familiar with NLP, it's one of the most popular place to go through. Basically, if you are looking for models or data set, you go to Hugging Face. This is the coverage. We cover a lot of the large institutional languages, like English, but then, basically the other one is like, it's left behind. Now, if we know that data set is the problem, then why don't we work on that, right? So it's costly, right? Creating data set is expensive. Working on NLP for those languages are expensive. However, according to Blasi, the people who can work on, at scale for these languages usually are, companies. They have budget to do that. University usually don't have enough budget to work on that. However, they don't really have an incentive to work on those languages because of economic factors, right? So if you have a budget, for example, if you're a company, you have a budget, okay, let's build some NLP technology, then fairly you're gonna go, okay, let's do German or basically languages that provide you more profit, right? If you were under like business meeting, okay, let's fund this NLP research for, I don't know, like Tagalog, for example. Well, it's not as interesting, right, in terms of business. Not only that, it's very hard to find speakers, right? So if you do have a budget and you would like to work on it, where do you get the speakers, right? So these are like Amazon Mechanical Turk, Upwork. These are common platform to find the speakers. I don't think you can find Maduri speaker there. Well, Maduris have 7 million speakers, by the way. It's like more than most of European. I think some of European language, but I don't think they are here, right? You won't find people that speak Maduris there. So basically, therefore, people who work on specific local languages are usually from the local institution itself. Right, so then how do we actually work for these underrepresented language? I would like to tell you a story and to compare. One is the conservative way on building data set for these languages. The other one is the open community-based movement. So quick background for Indonesian. It's one of the most populous country in the world. It has 700 languages, believe it or not. But then we don't have any it's very much limited in terms of NLP data. Right, so one of my work is NusaX. This is NLP dataset for Indonesian languages. The task was machine translation and sentiment analysis. The way we built this corpus is kind of conservative, where we have a group of researchers. It's like standard. Okay, let's do this research. We design, what type of data we would like to generate, what kind of tasks we would like to handle. How do you get the data? After that, okay, how much money we have. After that, okay, let's find people who can actually create the data for us. It's very standard, right? The difference is that the way we find this, that we have to go through internal connection, because it's very hard to find, speakers for these languages. So we post job advertising in the universities. We ask our friends, colleagues, social media, those type of way to find speakers. Once we got the data, and then after that, we determine what kind of experiments to run, what kind of model we train. After that, like we write the paper. So basically, the researcher one and the people who actually speak the language, we don't speak the language, by the way. Like we only speak 1 or 2 languages, but then the most of the languages we don't speak. It's basically disconnected, right? The speakers and the actual scientists are disconnected to each other, except for, we hire them to create the data and then we pay them. That's about it, right? And the research is basically private, right? Until we release the data to the GitHub. Now, we managed to gather for these languages. These are all low resource. However, we only get 10. It's not because we only limit to 10, but we only find speakers for those 10 languages. And we only have 1,000 per language. Because it's very expensive, it takes time, and the whole thing takes about like 1 year just to construct this corpus. So it's very slow. Now, the contrast, right? We have a movement called Nusa Crowd. This is basically the same motivation, where we would like to gather NLP dataset for Indonesian, but rather we make this open. So we have this open public, everybody can join, everybody knows the project. At least like if you Google that, you can find the projects. The pipe, well, okay, so why we do have a Nusa Crowd? Because as we mentioned before, local university actually do research on the languages, but for Indonesian context, sometimes they don't release it. Right, they just keep it by itself because partly they don't really in custom of releasing data set, but some other reason as well. So not only we would like to gather new data set, but we would like to connect to the university and ask them, hey, can you release our data set or not? Right. So that's our aim. The way the Nusa Crowd works, that we have a core team, which is like 5, 6 people. We design the general ideas. After that, we built the public repository, as you can see. Then after that, that's it. Everybody practically can participate, right? So we have like guideline on how you can participate. So for example, you can fill in the data card. If you're good at coding, you can code the Python data loader. You can release your own data set. You can ask people to release their own data set. They can ask universities. So we have like a lot of guidelines on how to participate. And not only that, we have bi-weekly meeting where it is also open for everyone to join. And the research was public. So for the beginning until the end, everybody can see the progress, what's going on. They can join and participate to the public meeting. In contrast to Nusa X, within like about 2 months, we get 100-something data sets, and in 19 languages. And not only for text, we managed to gather data for vision, language, and speech as well. Another example is Universal NER. This is actually still ongoing. So if you Google Universal NER, you can look at the website. As you can see here, this is community annotation effort, where if you are interested, you fill in the form, and then after that, you'll be invited to the Slack community. And after that, you'll basically have this tool to annotate your data on your languages, right? This is like, basically with this, you can scale up and generate multilingual data faster rather than, a traditional way where you hire people to do that. Those examples were project-based, so we have projects and then we open the projects, but we do have like communities that's more like, okay, region-based. For example, we have Masakane, where this is like community for people who are interested for African languages. Currently, we are also building one for Southeast Asian NLP. Different from the project-based, it is not bounded to one project, but rather it's a forum where people can discuss, they can share ideas, they can work on multiple projects at once. These are the examples from Masakane, where they publish some of the data sets. They release many African data sets. These are some examples. Right, and we do have more. For example, Big Science. We've heard Big Science and Bloom a couple of times today. They are also doing this as an open project, right? It's not private to Hugging Face only. Everybody can participate in Big Science. We have other initiatives as well as I've seen here. Right, so a big takeaway, I think community-based research is good for building multilingual NLP resource because we can connect to the native speakers easily, and we can talk to them. It is also great for collaboration because you can talk to people, you can discuss, you can share the ideas, and it's also minimal entry barrier. I think this is very important because if you want to join research normally, you have to be somehow affiliated, right? You have to be either a PhD student or like if it's industry, then you have to work there, right? But with open research, you can join without needing this requirement. Some challenges though. One thing that I noticed is about people and motivation. For example, here, Big Science in the, like the advertising, it says, oh yeah, we have 1,000 researchers. Cool, but then the actual paper, they only have like 300 something, right? So, the 700 is not really active. So in Big Science, specifically, they split the work into subcategories. Right, so this is one of the category, which is data sourcing that I was participating. So this is where we try to find where the training data is. So for this channel, we have like 100 people joining, but then for the weekly meeting, it's probably only like 10 people joining. So in practice, these are the people who actually contribute to data sourcing, right? That project is also one of the issue. For example, this is like real screenshot from one community. Oh yeah, I have a cool idea, but then like after that, and that's it, right? Conflict is also interesting because we have to deal with many people. The research works. We have some challenges. For example, after the research is done, then we discuss, okay, who's going to be the first author, and people can complain, oh yeah, I do more work than you, but I'm the first author, and also the last authorship, sometimes they fight about this. In terms of research direction also, sometimes some people have like agenda, I would like to direct this research to this direction, and we have to, there's some argument would happen at some point at time. Additionally, because the community-based movement is practically online, which is great in the sense that you don't have to meet up with people, it also means that, it is going to be tricky for many communities where internet is not easily accessible. And it sometimes happens that such community also the one where, we are underrepresented in terms of NLP research, right? So to wrap up the quick talk here, moving forward, I think we should have more focus on non-English research. And second one is more appreciation for non-English NLP, which is kind of connected. But the second point, what I meant is that usually when you have NLP research, right, it's either English or multilingual, including English. And sometimes if you work on specific languages, people can see that as second-level work compared to English. Well, why you are working on this language and not English? Sometimes it happens. So we need to, we don't have to have that mindset. So basically, other languages as equivalent as English, right? And lastly, I would like to suggest engagement with local communities because, for example, if you're interested on working for Arabic, for example, I think it's best to involve them, right? Because they know what's the problem, they know what's the challenge, and so on and so on, right? Not only that, it also helps them, to be exposed with research because sometimes, they don't have privilege to, participate in such a research, right? That's it. Thank you. And any question?
Okay, so, all right, so we have time for a couple of questions here. And my microphone is finally working. Okay, so actually I'm going to fire off a question that just randomly entered my head, which is, and I want to be told this is a terrible idea and to know the reason why, but when you're thinking about lower resource languages, right, what is the fundamental argument that stops someone from saying, okay, if a language at least has a translation module, like you showed for Javanese, right? May not have most of the other applications in NLP, but at least it has translation. What is stopping someone from, say, hypothetically taking the entire corpus of English internet data, translating that to Javanese, and using that as the data set to train a language model, right? I'm sure there's got to be plenty of bad reasons why you shouldn't do this, but the fact is it is possible, right? And so what are your thoughts on that, right?
Yeah, it is possible, and people do that. One of obvious reason is that, empty is not perfect, right? But, that's clear. But people do that anyway. I think it's kind of, in a sense, okay as a last resort if you want to do it fast and quick. But it's not going to be perfect because one of the main reasons is that you cannot transfer cultural information, right? So, in fact, let's assume that you use human to translate. Let's assume that human is perfect for translation, and we can argue about that. That's also not capturing the culture. For example, many of NLP datasets were multilingual, were produced by doing translation, but they translate from English. One real example is that we have QA dataset, right? Question answering. It was multilingual, but it was translated from English. The problem is the question is very US-centric, right? Like who won the Super Bowl? Like it's the Taylor Swift last album, right? If you translate that to Hindi, I don't think those people care so much about Super Bowl, for example. Now, the second one is about the cultural reference. For example, this is one very particular example. In English-speaking country, you say your heart is warm when you feel good, but I think in specific language, it's actually cold that if you feel good, right? Something that you cannot just simply get by translating.
Answer, and I think it does seem that, and as we think about meeting from both ends, right, for languages that are under-resourced, right, it seems that there must be a way to use information from other languages, but at the same time, it probably needs to be restricted to things that are incontrovertible facts that are of universal interest, such as translating mathematics from English to a low-resource language. That's still valuable and probably doesn't have a cultural difference or variation to it, right? At the same time, there is still the need for the kinds of efforts that you just described to collect information that could be perhaps focused on the elements that could not be captured by translation, right? I'm just trying to see how to think about what's the fastest way to get a low-resource language up to a suite of natural language tools that's a bit more comparable to the high-resource ones. So thank you for the answer. Okay. Any, yes, Neha?
Thank you, great talk. I actually had a question around because we also work with some low resource languages. So a lot of the data is locked in audio or image format. For example, Hindi. We have very little text, but there is a huge volume of Hindi movies, right, which have audio data. So I'm wondering, like, is there any research direction that aims to, because it's low resource even to transcribe that data?
Right, yeah, that's a good point, actually. It's not mentioned here, but many of those languages were not designed for writing purpose. They were mostly spoken language. So even if you have unlimited budget to transcribe, it's not going to be perfect because there is no guideline how to transcribe. For example, one particular language that we work for, Indonesian, we have different way to transcribe the same word because it sounds the same, and we don't know which one is the correct one. So one of the research direction is actually moving beyond textual NLP, but rather actually using the sound as it is rather than trying to transcribe, because it's not natural for some language to transcribe it. Yeah.
All right. Any last questions from the audience or online? Okay. Well, in that case, let's thank our speaker one more time. Okay. And with that, we have come to the close of day one of the Castle workshop. Of course, tomorrow we will have another set of sessions followed by the panel, and you are all welcome to join us again. And as for the rest of this evening activities, we have a dinner for the speakers and organizers. So I guess I'll be counting on you, Philip, to lead us to the buses where we will board and head back to the hotel for dinner. Okay. Well, first, let's